Okay, so this is a mini unit sort of thing that we have on some counting principles and some ideas that can help us set up for our probability unit. And so it's sort of a hodgepodge thrown together. So these are kind of really separate lessons that just sort of fall under one sort of small assignment that we do to make sure that we understand what's going on. Okay, so I'm going to introduce, and for some of you may have already seen this, Pascal's triangle, okay, and some of the patterns that are associated with that. And you may say to yourself, well, this is a cool pattern, there's a lot of really neat things that happen here, but in reality, what is it that makes this important? Well, from Pascal's triangle, there is a counting principle, and that counting principle we do use for some two-dimensional type counting, or what are called iterative processes. But it's also kind of important because where Pascal got the idea from has to do with something that we've been working on, which is combinations. But we'll get to that in a little bit. Okay, so first, Pascal's triangle. What's it all about? Well, Blaise Pascal figured it out when he was 13, or discovered, sort of looked at all these principles and found how they all went together and things like that. And it is a sequence, although it's a sequence that goes in two dimensions. It doesn't just go in a straight line. It's a sequence that goes in straight lines and then sort of downwards as well. So we have sort of two directions. One direction kind of goes diagonally, okay, and this is called a column. Okay, so that would be a column. Okay, and the other direction goes horizontally, and that's what we'll call a row. Now, for terms, these are terms are something that we use to describe an expression or a numerical value or algebraic value in a sequence or in a particular pattern or relationship. And as a result, there are terms in here. The term is denoted by two positions. So the column is given the letter R, and it seems kind of random that it's the letter R, and the row is given the letter N. N and R we've seen before. We usually use N to describe the number of elements in a set, and R we use to describe the number of positions that we're going to use, or the number of individuals that we're going to select for a grouping. And that's not lost, okay? So we're going to come back to that idea. But what we do is we use this as to sort of locate a position, and that's really what a term is. A term is a value that's associated with a position in a sequence, okay? And so the N and the R sort of tell you where it is. Now, what's strange is that when we start our positioning, usually you would start a row you would figure this would be row number 1. That would be row number 2, row number 3, and just sort of go from there. But this is actually row number 0. Okay, and here it is, here, row number 0. And heading all the way down as you go down each row, we've got 9 rows right here in this Pascal's triangle listing that we have here. But we also have columns, and the columns also start at 0. So this is column 0. That's 0, and then that's going to be 1, and that's going to be 2. So R is equal to 1, R is equal to 2, and so on and so forth. So for example, this term right here, if I was just to pick a random term, that would be term, and it would be row number 0, 1, 2, 3, 4, 5, 6. Okay, so 6. And then it would be column number, 0, 1, 2, 3. Column number 3. Okay, or T63. Now there's a relationship between T and R and another value. So we'll come back to that, or we'll come to understand what that is. But there's some really neat, there's all kinds of patterns in Pascal's triangle, and they have to do with where these numbers come from. But before we go any further, what we do want to look at one specific idea, which is one specific pattern, which is Pascal's method. Excuse me. Pascal's method takes two numbers, okay, and this is a neat pattern because you can generate Pascal's triangle using it. You take these two numbers and it actually equals, if you add them up, it actually equals the number below it in between the two numbers. So, start simply. 3 plus 3 equals 6, okay? Or, I don't know, 1 plus 6 will give you 7. Okay, even if you go outside of Pascal's triangle, You know, 1 plus 0 will give you 1. Okay? I know that there isn't a number out there. There isn't a 0 out there. And in fact, there isn't anything out there. But still, this iterative process, or this process that allows one value to help you determine what the next value is, kind of like a recursive formula for those of you guys who took grade 11 UMath. That recursive formula kind of shows you what's happening next. Okay? And you can use what's previously stated to go from there. So if I wanted to do the next line in Pascal's triangle, I could go 9 plus 1, which is 10. I got to write small here. 36 plus 9 is 45. 84 plus 36 is, what is that, 120. 126 plus 84 is 210. Okay, again, I'm just adding these guys. I add these guys, and it's going to be, what, 252. Then I add these guys, and it's 210. And I add these guys, and I get 120. Add these guys, I get 45. Add these guys, I get 10. And then we have a 1 and a 1. Now, what this does show you is that there's a neat pattern. You probably noticed it as I was going across. In using this sort of additive principle, or what we call Pascal's method, this idea that these two numbers will give you this number, is that you'll notice it goes 1, 10, 45, 120, 210, 252. Then it starts going back down again. But when it goes back down again, it's exactly the same on both sides. So what I will talk to you about are some patterns that exist in Pascal's triangle. Okay? After we get to know that idea. Also, Pascal's method can be written using term notation, although it's a little bit complicated. Okay, so if we take TNR, we should be able to take the term above it and another term above it. So the term above it is n minus 1 because it's a row above. So if this is TNR, this 28, I take the term above it. Okay, or if I'm talking about this in general, that's TNR. Okay, then I take the term above it and the term above it, and I add them up, and it equals to this. So the term above is going to be n minus 1. This term above is also going to be n minus 1. This is in the same row, and this is the row before it. Okay, and that's where the formula comes from, and that's what this is all about. It looks very complicated, but the idea is that it's sort of a mathematical principle or a formula that works all throughout Pascal's triangle, and of course, it works for the things where this comes from. But again, we'll come back to that idea. Okay? All right, so what we'll do is we'll look at a few patterns in Pascal's triangle, and I'm not going to necessarily go through all of these with you directly, but I am going to sort of show you these and then show you other ones. First of all, the sum of each row. So if you're to take each row in Pascal's triangle, and we kind of need to have Pascal's triangle in front of us. So here, I've got a good copy version of Pascal's triangle here. Okay, so we'll use that one. All right, so if we're going to do the sum of each row, it's kind of big, but that's okay, we'll figure it out. The sum of each row, then if we add up all these numbers, what do they add up to? Well, if we take the first row, so we'll go row, and then we'll go sum. And so if my row is 0, well, it just adds up to 1. That's not difficult. Row 2, 1 plus 1. Sorry, row 1 is 1 plus 1, which is 2. Row 2 is 1 plus 2 plus 1, which is 1 plus 2 plus 1 is 4. And then row 3 is 1 plus 3 plus 3 plus 1. Okay, which is 1 plus 3 is 4, 5, 6, 7, 8. Row 4, I'm kind of playing at this. 1, 4, 6, 4, 1 actually adds to 16. Row 5 adds to 32. Row 6 adds to 64. And hopefully you can see this pattern that it doubles each time. Or if you know it more exclusively, then if you take the sum of a row in Pascal's triangle, it's equal to 2 to the power of n, where n is the row number. Which is kind of cool, kind of interesting. Okay, and that means that each one of these rows adds up to 2 to the whatever. Okay, so if this is row 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this row, bottom row here, so row 10, okay, should add to 2 to the 10, which is, off the top of my head, I should know that, 32 times 32, 1,024. Let me just make sure. 2, It's a little early in the morning here, so I mean I have my brain working right. 1,024. Okay, and so that's kind of a cool principle that exists there. All right, for Pascal's triangle. There's also kind of a neat one that has to do with the perfect. Let me just fold that for now because I'm not going to use this one other than just to view it. Okay, so for the next one, perfect squares. Okay, or what we call triangular numbers. All right, now there's actually two patterns that exist here. So one pattern that exists here is you've got these things called the perfect square. So if you take this row right here, okay, you take column 1, and you square it. 1 squared is equal to this number plus the, well, there's no number there, so maybe we'll start the pattern here. 2 squared is equal to 1 plus 3. Do you see how that works? Okay. So 2 squared, which is 4, is equal to 1 plus 3, which is 4. Or if you, I don't know, slide down to 4. 4 squared is equal to 6 plus 10, which is 16. Or I don't know, 7 squared, which we know is 49, is equal to 21 plus 28. Okay? And that's kind of a neat number. But more importantly, if we take a term in row 1, because we really should write this pattern down and go along with it other than just looking at the actual pattern itself. Well, we have these things called triangular numbers. Okay, so triangular numbers, first of all, that's a triangular number. That's the number triangular number 1. And we have another triangular number, which is the number 3. We have another triangular number, and these are numbers when sort of stacked, they form a triangle. And another triangular number. Put that over a little further. 10. So 1, 3, 6, 10. And you'll see, of course, that that's going to be row 2. Now, row 2. Okay, so the relationship between perfect squares and triangular numbers is if we take row 1, or T, and it can be any row, n, comma 1, and we square it, so we take this row, boop, and we square it, that's equal to T, it's equal to the number that's diagonal to it. So Tn, comma 2 plus the one that's kind of below it. So Tn plus 1, comma 2 as well. Okay, and if you add those two together, okay, now these are your triangular numbers. And this are perfect squares. So that the triangular numbers, or row 2, okay, can kind of be used to predict your perfect squares. Your perfect squares, I guess, can be broken up into the sum of two numbers that are triangular numbers. Okay, kind of a neat idea. I mean, these are all patterns. So we'll talk more about the specific patterns, and we'll go through a bigger example of that. So I'll press pause. Okay, you can have a look at that. Okay, and then go from there. All right, powers of 11. This one's actually pretty cool. Okay, and so what it has to do with is 11 to particular powers. 11 to the 0, 11 to the 1, 11 to the 2. And you can go ahead and start figuring those out if you want to. We'll do it in a sec. I want to have it all out here. Okay, and it has to do with the rows of Pascal's triangle. First of all, 11 to the 0 is, I'm going to put it all the way over here. I know it seems silly, 1. 11 to the 1 is 11. 11 to the 2 is 121. 11 to the 3, you may have to do that in your calculator. All right, 11. Okay, 1331. And I know that you're probably noticing, or hopefully you're probably noticing the pattern that exists here. And I can use Pascal's triangle because it's 1, 4, 6, 4, 1. And you can try it, 11 to the 4. By the x4. 1, 4, 6, 4, 1. Okay, so these are actually Pascal's triangle, which is kind of cool. All right, and where this comes from is a little bit more interesting too. But the idea is when we take these sort of rows, and we take the powers of 11, they actually equal each other. Now, there's a problem that we run into. And the problem that we want to run into is when we do 11 to the power 5, it doesn't equal the row in Pascal's triangle. It's 1, 5, 10, 10, 5, 1. This is 1, 6, 1, 0, 5, 1. So how does that work? Okay, how can we still use Pascal's triangle and get this 161051? Well, remember, multiplying by 11, okay, what you do is, if you do powers, remember, you multiply, like this is, for example, just 11, okay? But this is 11 times 11. So if I take this row and I times it by 11, what do I end up doing? Well, what I end up doing is I have that row. So I have, if I times something by 11, I really times it by 10. Sorry. So when I times 11 by 10, so again, I want to do 11 squared. When I times 11 by 10, okay, I get 110, right? Okay, and then when I times it by 1, I get 11. Okay, so this is 11 times 10, and this is 11 times 1. And of course, to get 11 times 11, we just have to add them up. Okay, so we add them up. And what you'll see is I get 1, 2, 1. Okay, and so as a result, that's sort of where that comes from. Well, if I want to do 11 cubed, get this out of the way for now. My cat's just annoying us here, but that's all right. We'll just let him talk away. He'll eventually be quiet. So for 11 cubed, I take 121 and I times it by 10, right? And I get 1, 1, 2, 0. Sorry, 1, 2, 1, 0. 1,210. And then I also get 121. And that's, times by 1, times by 10, times by 1. That's how you multiply by 11. And so if you take the row above it and the row below it and add them up, you'll actually get 1, 3, 1, which of course is how we multiply by 11. We don't usually do it that way, but it's a trick to multiply in your head. To multiply something by 10 and then multiply something by the ones column as well. But what you'll see is actually 11 cubed is the row above it and the row below it. Okay? You may say to yourself, well, that doesn't make any sense. How does that work? But the idea is that I can use the row above it to figure out the row below it. Okay, by knowing that I'm going to have something in the tens column and then something in the ones column. So let me show you how that works. Okay, so we're going to do 11 to the 5. Okay, now to get 11 to the 5, we know it's going to be associated with this row right here. Okay, the problem, the way that this row is communicated is, if I have something in the ones column, okay, then I put it in the ones column. If I have something in the fives column, I put it in the fives column. The problem is I have a 10. Okay, I have a 10 in the hundreds column, and you can't put a 10 in the hundreds column, right? Because it's 2 digits. So for the next column, it's going to be a 0. I use the right hand side, and I take the 10, which is actually 10 hundreds, which is 1,000, and I add it into this column right next to it. Okay, so that this 10 right here actually becomes 11. Now again, I run into the same problem. I can't put 11 into a single column. So what I do is I take that 1 and I add it to the next one, 6. And then the 6 is fine. The 6 is a single digit, so it can go in that column. So then what I do, I just have the 1 in the front, and I got 160151, which is 161051, which is 11 to the power of 5. Okay, we can do it again for the next one, 11 to the power of 6. And we get 1771561, okay? But again, I can use Pascal's triangle in order to do that. Okay, this is again 11 to the 6. This row 6, so we have 1s in the 1 column. And these are the number that we have in the tens column, 6. And this is the number that we have in the hundreds column, but we can't put 15 in the hundreds column. We can only put 5 in the hundreds column because it's 1500, 5 hundreds, and then the 10 hundreds is actually 1,000, so I put it in the thousands column, which is 21. And then I take the 2, and because we can't have 2 in the thousands column, we can only have 1 digit, which is the 1 in the thousands column. We take the 2 and we put it here, the 7. And of course it's 17. We can't have 17 in the 1, 2, 10, hundreds, thousands, 10,000s column. So we have to take that 1 and bring it into the next column, bring it into where it should be in the 100,000s. Okay, and then that's a 7. And then finally we can have 7 in that column, which is fine. So we don't need to carry anything over into the millions column. And we end up with, oops, sorry, that's boo-boo. 1. We end up with 1651771. 1651771. I'll do it one more time. It starts to get a little crazy once we get into the bigger digits here and finally in the 126s, but it still works. So again, for 11 to the power of 7, it's going to be 1, 7. 21, I have a 1, and I carry the 2 over here. So that becomes 37. Okay, take the 3 and carry the 3 over here, so that becomes 38. Carry the 3, 38, and then take that 3 and carry it over here, 3, and that becomes a 4. And then take the 2 and carry it over here, and that becomes a 9. And then take the, we don't have to carry the 7, and then we've got a 1. And we go ahead and we figure out what 11 to the power of 7 is. Okay, and it's 19487, 19487, 171, 171. So that's kind of a cool pattern. Okay, and again, these are just interesting patterns of Pascal's triangle. What they do have to do with what we're doing is that Pascal's triangle comes from something very specific. So let's go over a few more of these neat patterns that exist. Okay, and then we'll get to Pascal's, well, where Pascal's triangle comes from, and then we'll get to Pascal's method. So in your notes, and this is very important that you check your notes and at least print this one out, there's all kinds of patterns that exist. Okay, so I'll talk to you about what each of these are. Some of them we've already done. Okay, so each row starts and begins with a 1. Okay, and that's key. It's just I call it a tent of ones because it's kind of like a tent, okay? But whatever. Each row begins and ends with a 1. Column number 1 equals the row number, okay? So that's another interesting feature. If you want to know the actual row number that you're in, all you have to do is look at the second number, and I know this is row number 9. Or for that matter, the second last number, that's row number 9. Okay, so if my row starts 127, then I know I'm in row 27. Okay, so that's column number 1 is your row number. Okay, the sum of the terms in a row are equal to 2 to the power of n. That's a really important one, which means, of course, the sum of all of these is 2 to the power of n. Okay? We've already done that one. That was one that we already did together. Each row is palindromic, okay? And that means that it starts, okay, in one way and it finishes sort of in the reverse way. So a good example of a palindrome would be radar. Radar is the same read forwards and backwards, okay? R-A-D-A-R, R-A-D-A-R. Okay, so let's start simpler. 1331, that's an easy one. 1510, 1051. Go all the way down to the bottom. 110, 45, 120, 210, 252. And then it goes back down to 210, 120, 45, 10, 1. Okay, so it's palindromic. Now, column number 2, these are your triangular numbers. Okay. The square of column number 1 is equal to the sum of these two. So that's the relationship between triangular numbers and the perfect squares. Okay, we already did that one. One that's really cool, very sort of Canadian, I suppose, is hockey stick. And that's kind of a neat idea. So if you start at an edge, whether it's the right edge or the left edge, doesn't make a difference, and you start adding the numbers in a diagonal, okay? Wherever you stop, if you're zigging this way and you zag the other way, that's what the sum is going to equal. So in this example here, if I take 1 plus 3 plus 6 plus 10, 1 plus 3 is 4, plus 6 is 10, plus 10 more is 20, it equals 20. Okay, and it works, if you go in the other direction too. I'll take this one, and I'm not going to do too many because I have to add in my head, but 1 plus 6 is 7, plus 21 is 28, plus 56 is, and I don't even have to figure that out because I know it's 84, but 1 plus 6 is 7, plus 21 is 28, plus 56 is 7, 84. Okay, so if you go this way, and then you zag, that's what the sum of that row is. And it works in the other direction too. Okay, obviously because it's palindromic, it works in both directions. So whether you start from the right or you start from the left, and you zig all the way down, and then if you decide to zag and go in the other direction, and be able to find the sum of that row. Okay, powers of 11. Okay, powers of 11 have to do with, or can be figured out, or figured out from the row number, as long as you use each digit as each successive column, and then carry the values into the next column. Okay. There's many others. Okay, there's many, many other patterns that exist. And there's all kinds of fractals and really cool number patterns that exist in here. So you can look them up online. There's websites, and I'm sure there's conspiracy theories and stuff having to do with Pascal's triangle, whatever. The key is this. Where does Pascal's triangle come from? And this is where it comes from. T and R, the N and the R is not a coincidence. Although for sequences, we did call it T and N. Okay, if we have a single sequence like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, it is called TN. For those of you guys who took grade 11U math, you know what I'm talking about. Okay, this is a unit on sequences and series, and the value, the position of a term TN, if it's the fifth term, it's T5. Okay, it's the same idea for these terms, except it's two-dimensional, N and then R. Okay, but T and R is NCR. In fact, NCR and the letters that we use for NCR actually came from a term or from sequences, but more exclusively, Pascal's triangle is created by chooses. And that is key. Okay, so that means that all of these patterns, not only are patterns in Pascal's triangle, but they're all patterns for chooses. Okay, so take a couple of seconds to think about that and realize that when we choose elements, okay, T10, 5, okay, so T10, 5, 0, 1, 2, 3, 4, 5. T10, 5, 252. Okay, so you can actually figure out any row in Pascal's triangle just by starting your chooses at 0, and then going 1, and then going 2, and then going 3, and then going 4, and then going 5, and 6, and 7, 8, 9, 10. So if I wanted to, I could take, and I got to have my calculator handy because you got to be able to do these chooses, but I could do the next row in Pascal's triangle here by going 11, choose 0, which is of course 1, and an 11, choose 1, which is 11, and 11, choose 2, which is 55, and 11, choose 3, which I won't know off the top of my head. I should, but I don't. Getting old. Okay, choose 3. Okay, it's 165. And 11, choose 4. 11, again, this is a bit onerous of a task, 330. And we'll use Pascal's method to figure it out. 1 plus 10 is 11. 10 plus 45 is 55. 45 plus 120 is 165. 120 plus 210 is 330. And so on. And I also know it's going to finish at 11, choose 11. And 11, choose 10. And 11, choose 2. Oh, sorry, choose 10. Choose 9. And 11, choose 8. And that's 165. And 11, choose 7, which is 330. And so you know that with the palindromic idea, that's important. It also introduces a principle for combinations. And that is, if you have 11 elements and you choose none of them, that's the same thing as having 11 elements and choosing all of them. There's the same number of ways in which you could do it. More importantly, if you have 11 people and you choose one for a group, it's the same thing as having 11 people and choosing 10. Think about that. There's 11 people that you're choosing, okay, I don't know, to go on a trip with you or something. You have 11 friends, okay? You have to pick one person to leave out, okay? Or if you have 11, choose 10. There's 11 people, you're choosing 10 people, and you're leaving one person out. So it's actually the same process, okay, even though the numbers are sort of different that are being used for that scenario. Okay, and that's an important idea, and so that's allotted in here. So there's all kinds, the sum of a row. If we take, 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6. That's 2 to the n. And that formula that we used last unit for 2 to the n minus 1, that's just this row, but not having 0 of them. So you take away this 1, and there it is. That's your formula. Okay, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6. That's if you have 6 elements and you're taking some of them. You can't take 0, so you take 1 of them, or 2 of them, or 3 of them, or 4 of them, or 5 of them, or 6 of them. And so 2 to the n is that, the whole row including the 1, and 2 to the n minus 1 is the whole row minus the 1. Okay, so it's a pretty important idea. I don't want to make this too messy in case I want to scan this again and put it in my notes, or if I lose it or whatever. Okay, so that's a good, check out that good copy version, okay, of Pascal's triangle with all those principles in there. Okay, And just to go over, I guess I'll actually just use your notes to go over this. This is just what I've been talking about all along. And that each row in Pascal's triangle 1, 2, 1 is actually chooses. 1, 3, 3, 1 is 3 choose 1, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, and so on. Here's where I do row 11 and I figure it all out. Okay? What we're going to do now is we're going to apply Pascal's method. Okay? And the way that we apply Pascal's method is twofold. First of all, we can just look at it as a numbers sort of game. All right? So if I look at T2311, okay, remember that any term is going to be the two terms above it. Okay, so I've got it kind of diagrammed here. T2311 right there, okay, is going to be the term above it. So that's going to be a term above it and the term above it. Okay, diagonally to the right and diagonally to the left. This is going to be 22. That's the term above it. And then this is in the same row, so it's going to be 11 and it's going to be 10. Now what's more interesting with that is it's actually also going to be chooses. Okay? So in other words, we can actually just use chooses in our calculator without having to look at Pascal's triangle. Okay, if we take T2311 and we go 23 choose 11, it's going to be equal to 22 choose 10 plus 22 choose 11. And so all these patterns in Pascal's triangle do have to do with chooses as well. Okay, so have a quick read at that, okay, in your notes and go from there, okay? And then we're going to look at our first iterative process. So let me use this Pascal's method idea, okay, to sort of map this out. This is more important for the chooses. So 24 choose 8, okay, is equal to, I probably should have made these circles a little bigger because I can't write that small. 24 choose 8 is equal to that one plus that one. Okay, so a choose plus a choose. This is 24, so this is 23 and 23. And then 8 is going to go here to be in the same column, and then 7 the column before that. Okay, so 24 choose 8 is really 23 choose 7 plus 23 choose 8. Okay, we can also take these two values, which will be the ones that are above, here and here, and add them up and we can predict what it equals, which is the one down here. So 45 choose 22 and 45 choose 23 side by side in Pascal's triangle are going to be 46 choose 23 or 46 choose 23. You can always sort of even do a subtractive method. This is a little bit weirder, this one here. I'm going to do this over here so I have room. So this is 71 choose 36 and this is 70 choose 36. So there's 70. 71 is going to be down here. Okay, 36 and 36 because they're both in the same row. The 71 choose 36 here. So if I take this and I subtract this, well, this plus this equals this. So this minus this is going to equal this. So we've got 70 choose 35. And that's sort of a bit of that counting principle and how it works. A little bit quirky, a little bit weird. Some of you, I'm sure, will ask me to take up a few of those questions that we do in our homework. Okay, but this is really the be-all, end-all as far as our counting principles. So when we take Pascal's triangle and we bring it down to a counting principle, it has to do with one of these building processes, or what we call iterative processes. Okay, so when we do this, Kevin lives 5 blocks south and 4 blocks east of Tim. So here's Kevin. Okay, he wants to get to Tim's house. Tim is up here. Okay, so how many different ways can Tim travel to Kevin's house? So this is where Tim is and he's going to go to Kevin's house. My mistake. Okay, so I got to read the question carefully. All right, so how many different ways can he get from here to here? Well, if we start small and work our way forward, and this is really what this is, an iterative process is a step-by-step process, then really, if we say to ourselves, well, if he's going to start in the spot, okay, he's starting at 0, right? There's 0 ways for him to get there because that's where he's starting. But he can either go this way or this way. He has to travel along these blocks, okay? Maybe it's a car and this is a road system, okay? So if he goes this way, there's only one way for him to get to this spot and only one way for him to get to this spot. Okay, so if we look at how he can get just to this spot here, he could go this way or this way. So the answer here we know is 2, okay, just because it's simple. But what about going to, for example, let's say he's going to go sort of zig and zag and find his way to Kevin's house. What about here? How many different ways can he go here? Okay, well, he can go 1, 2, 3, 4. Now, even that, a lot of people may not have seen those ziggy-zaggy ways. Depends how clever you are. And of course, there is a rule here. And the rule is you always have to make progress towards your target. You can't backtrack. If you can backtrack and allow yourself to do that, to get lost and to backtrack, then there's an infinite number of ways for you to get to Kevin's house. Because you can backtrack and go forward and go backwards and forwards and backwards and get lost and go back. And there's an infinite number of ways in which you can get there. But if I want to find out the number of ways for me to get there, only moving in the correct direction, in this case east and south, okay, then I have to be able to sort of say, well, this is the minimum sort of amount of steps for me to get there, the minimum number of ways for me to get there. Okay, now for me to get to here, it's going to be pretty crazy. Okay, I got to go this way, this way. What else do I do? I guess I could go this way and so on. And I don't even know if that's right, because I can go zig, I can go zag, I can go zig, I can go zag, then I can go ziggity zaggity and ziggity zag. It's not even 4, is it? There's got to be a better way to do this. And there is. And what that is just to figure out small parts of the trip and say, well, if up to this point there's only one way for me to get there, and up to this point there's only one way for me to get here, then I can only just add those two together in order to get that. And that's the idea. Okay? If I take this step, which I do know for sure is correct, which is 2, and I know there's only 2 ways to get there because it's simple, then I know it's a sum of this way and this way. He could go this way, or he could go this way. The only way for that to get into this one's particular location, okay, is to feed together. So this 1 plus 1 gives me my 2. Okay, now for him to go this way, there's only one way for him to go this way. In other words, I can only go from this spot and follow those rules, and there's only one way for me to do it. Okay, to come from here, there's only one way. So to go to here, there's only one way. Or if you know it, straight to that spot. Similarly, this is also, to go to here, there's only one way that you can get there. There's no other way to feed in there, and you can't go backwards. Okay, so there's only one way for you to get to this spot and one way for you to get to this spot. Okay? And if I want to get to here, I know that it's going to be a combination of I can either go to here or here. There's no other way that I can get to this particular location. So 1 plus 2 is going to be 3. And again, my goal is to figure out how I can get to this spot in the middle. Now again, if there's only one way for me to get to here and only one way for me to get to here to go straight ahead, then there's 3 ways for me to get to here. Now we can count those 3 ways if you don't trust the method, but past that it's just going to get too crazy. And you'll start either double counting or undercounting or having to use 15 different colors of pencil crayons in order to trace it all out. So to get to this spot here, I can go this way. Okay, that's 1. I could go this way, that's 2, or I could zigzag, that's 3. Okay, same idea to get to here. There's this way, and then there's the zigzag. That's it. Now, if there's 3 ways to get to this way and 3 ways to get to this way, how many ways are there for me to get to here? 6. I originally said 4 because I undercounted things. I didn't look at all the complexities that exist. But remember, 1, 2, 3, 4, zigzag, 5, and other zigzag, 6. But I can just use the 2 paths that lead into this thing. So if I look at what happened before, I can use that as a way to tell me what happens next. To get to this point, there's only one way to get to this point, from this previous point, which came from this previous point, which came from here. So there's only one way for me to get to here. Technically, this isn't 0. Technically, this is 1. Okay? But anyway, whatever. Okay? So 1 from this way and 3 ways from this way give me 4. And you can count them out. 1, 2, 3, 4. But you trust in the method. Okay? This is 1, this is 1, and these are all sort of, this is like the tent of ones for Pascal's triangle. Okay? And then 1 and 4 is 5. 5 and 1 is 6. 5. Okay? 4 to get to here, 6 to get to here. They feed in together to give me 10. 4 to get to here, 6 to get to here. They feed together to give me 10. 15, 21, 20, 15, 35, 35. And of course, you're still seeing Pascal's triangle, just the center part of it. You see 6, 5, 20, 15. If there was another block, this would be 6, and so on and so on. Okay, that's going to be 70. That's going to be 56, and that's going to be 126. So therefore, there's 126 ways to get to Kevin's house. And that's the idea. Okay? And that's that iterative process where we use what happened up to that point to help us get to the next location. Okay? So let's use that counting principle and a couple other of these. Now for this one, I'm going to get you started. I'm going to let you finish it off, and then I'll show you the good copy answer. Mostly because it just takes a long time to add. And try to remember that if I made a boo-boo here, if for whatever reason I went 6 plus 4 is 9 or 11, that means everything after that is going to be wrong. Well, not everything, but everything that's affected by that particular number is going to be wrong. Okay, so you have to be careful that you're adding correctly, and that's also where I can get into these pitfalls. But this is a nice question. It's also got a couple of roadblocks, so I'll show you how to get past the roadblocks. Okay, so we start from this place, and we go 1, 1, 2. Nothing new. 1, 1. Again, there's 1 from this way, nothing from this way. 1 and 2 give me 3. 2 and 1 give me 3, and then just 1. Okay, 1 and 3 give me 4. That's kind of ugly, 3. 3 and 3 give me 6. 1 and 3 give me 4. 1 and 4 give me 5. 4 and 6 give me 10. 4 and 6 give me 10. 4 and 1 give me 5, and then 1. Okay, that gives me 6. 1 and 5 gives me 6. 5 and 10 gives me 15. 10 and 10 gives me 20. 5 and 1 gives me 15. 5 and 1 gives me 6. Okay? 1 and 6 gives me 7. 6 and 15 gives me 21. 15 and 20 gives me 30. 20 and 15 35. So you got to be careful. 35. 15 and 20 gives me 35. When you start getting robotic, that's when you start making mistakes. Okay, so take your time. Okay, now this is where we start getting to a roadblock. This sort of place where we don't have a road, and you just have to follow the paths. 1 and 7 give me 8. Okay, 7 and 21 give me 28. 21 and 35 give me 56. And now when I go to do this one, it's a bit more interesting because I can't add this 35 in here. There's no road to get me there. Okay, let's say, I don't know, the road is under construction or something in downtown Toronto. So as a result, we can't use that road. So how many, well, I can get there not from this way, so that's cut off, but I can get there this way. So this would be 35. And we'll fall away from Pascal's triangle and that pattern that exists, but we're still using Pascal's method. 35 and 21 is 56. 21 and 7 is 28. 7 and 1 is 8. And there's a 1 there. That's going to be 9. That's going to be 28 and 8 is 36. 56 and 28 is going to be 70, 84. And then 35 and 56 is also going to be, 35 and 56 is 80, 91. Let me just make sure I got that right because my eyes are getting old. Okay. And then go from, oh, by the way, I'm going from A to B. Okay. And then 56 and 35 is 80, 91 as well. 56 and 35, 91. Yep, I'm just making sure my heading's right. Okay, 28 and 56 is going to be 84. 8 and 28 is going to be 36. And then 1 and 8 is going to be 9. Okay, and you just sort of work your way through it. Okay, now what I've done here for you is I've done the wrong direction. I went from A to B. You don't always go from left to top left to bottom right. Here, this example, I go from top right to bottom left, and it doesn't make a difference. So you can try your best to go from top right to bottom left and look to see if you get the right answer. Okay? Again, watching to make sure that every path is available to lead you into that particular value. Okay, now for this one, a checker can only travel diagonally downwards. Once it reaches the other, it can be kinged. So this is where we want to go. We want to get kinged. Okay, and that means you put another checker on top, and then that checker can move backwards. Checkers can only move in this direction, and they can only move diagonal. Okay, so I'm going to put your piece right here, and I'm going to make this the same as the other one, and I'm going to put opposing pieces. I'm going to make them hollow, so that would be the opposing color. Just a different color, the other team. Okay? And so as a result, this piece is going to move around. Now, it can either move diagonally this way or this way. So there's only one way for it to go, either that way or that way. And so that's our iterative process. Okay? Now, it could also go this way, or it could go together, too. Now, the way it works in checkers is you can jump over a piece. And actually, when you jump over a piece, you take the piece off the board. You kind of, I don't know, kill it or eliminate it, whatever it may be. So for me to go here, again, same idea. Okay, one to feed in this way, so one. I get a one feeding in this way, and there's two ways to get to this way. So one way from here or two ways from here gives me three ways to get to that spot. Now remember, this is a checker, not a zero. Maybe I'll put like little hatchings on it. So it's still different. Okay, maybe I'll make them cross hatchings. Okay, so it looks like checkers and, I don't know, cross hatchings and then solids. Okay, anyway, and so when I go excuse me, to this next spot here, well, this would just be one and then one. When I go to this next spot right here, okay, there's two ways that I could get there. I could get there this way, which is easy, 3, but I could also jump over the checker, and there was one way for me to get to here, which means there's 4 ways for me to get to here. Okay, similarly, I take this 1 feeding into this square, and this 2 jumping over feeding into this square to give me 3. Also, you know, with the same principle, no checker in the way. There was 3 ways for me to get to here. There's 1 way for me to get to here, so there must be 4 ways for me to get to that next spot. Okay, this then goes to there. This then feeds in 4 to get to this way, 3 to get to this way, gives me 7. 4 this way, 1 this way, gives me 4. Okay, now for this one again, another check. Make sure, see if you know what to do. 4 from this way, and then, that's right, 4 from that way. Okay, gives me 8. Okay, and then 4 from this way, and 7 from this way gives me 11. 7 from this way, and 4 from this way gives me 11. And then 4 from this way gives me 4. That gives me 15. That gives me 22. That gives me 19. And that gives me 8. Okay? And so that's the idea. Oops, I just realized I made a boo-boo on my answer key. I should fix that. Okay, so if you're looking at your answers, you're like, hey, wait a minute, Henley did something different. Yeah, this should be an 8. Notes. You can go ahead and change that, and it shows that I guess I'm a little bit human. Okay, that's going to change these 2 numbers. This number should be an 8, and this number should be a 19. Okay, and so change that to an 8, change that to a 19. Okay, now what does that mean? Well, if I want to get kinged, I just want to get down to this row. So there's multiple ways for me to get down to this row. I could get down to this row here, which is 8. Or I could get down to this row here, which is 19. Or I can get down to here, which is 22. Or I could get down to here, which is 15. Or I go 8 plus 19, because it's an or, plus 22, plus 15, one or the other, equals a total of 80. Okay, so therefore there's 80 ways to get kinged. Okay, or to get down to that bottom row. Okay? Not 80 ways. I looked at the old sum. You're like, oh, that doesn't make sense. Okay, 8 and 19 is 27. Excuse me, plus 22 is 59. 60, 74. Okay, I think that's right. 8 is 27. 49 plus 15 is 64. That's a little bit better. Okay, and so there you go from there. And I'm, of course, going to correct this. Okay, so these are your notes. Notice that they're green and pink. You'll see them in the notes, at least when you see them online. If you print them out, they're probably black and white. Okay, but 8 and 19 is 27, plus 22 is 49, plus 15 is 59, 64. So that should be 64 and 64. Okay, so make that quick correction. All right. So that's how that we use that iterative process. That's how we go through that process. You do have some homework where it's a bunch of these things. There is some homework also having to do with Pascal's method. So there's 2 sets of homework for this scenario here. So have a look at that, at what's posted in our Google Classroom in the description, and go from there. Okay, have fun.